We're going to have a look at velocity time graphs. Now, these look very similar to distance time graphs. You should watch that video first before you watch this one. If we look at the axes, we have different units. So on the x-axis at the bottom, we still have time. But the difference is on the y-axis, we don't have a distance here. What we have is m/s, which means meters per second. So what we have there is a speed. So we say a velocity time graph. Velocity is maybe a more mathematical word for speed. If you look at question 1, as the graph rises, what this shows is that the ball is speeding up. It's getting faster. So it's 0 seconds, it's at 0 meters per second. It isn't moving. But after 1 second, it's now halfway through its speeding up and it's at 1 meters per second. And then at the peak, which finished speeding up at 2 seconds, if you look across, it's at 2 meters per second. So the speed is increasing as you go up the green line. And then what happens when you throw a ball? Well, it's going to speed up and then it's going to slow down. And so the second part is that it's slowing down. So for that, for example, you might have thrown it, you might have kicked it, it's sped up, it's going faster, then it runs out of energy, friction takes over, and it starts to slow down. So the first question is, how long was the ball traveling for? So the ball started traveling at 0 seconds, and it finished traveling at 4 seconds. At the start of its journey at 0 seconds, it's at 0 meters per second, it's not moving. And at the end of its journey at 4 seconds, again, it's at 0 meters per second again, it has stopped moving. And in between those 2 points, it's moving at a speed that isn't 0. It's been traveling for 4 seconds. Moving on to question 2, look at what's happening first. So the ball is speeding up, it's getting faster and faster and faster until it reaches 6 meters per second. And then it starts to slow down with slower and slower and slower until it hits 0 meters per second. And after that, it continues to be at 0 meters per second. The ball is stationary. Now, the question says, how long has a ball been accelerating for? So, accelerating is a word for the green part of the journey where it's speeding up, starting at 0 seconds and ending at 4 seconds. So, it's been accelerating for 4 seconds. Now, question 3 is kind of the opposite question. So, again, we have a ball, it's speeding up from 0 meters per second to 2 meters per second, and then it starts to slowly slow down from 2 meters per second all the way back down to 0. Now, we're being asked how long did it take for the ball to decelerate? So, acceleration is a green section where it's getting faster. Deceleration is a pink section where it's getting slower. Starting at 2 seconds and ending at 9 seconds. So, between 2 and 9, that was traveling for 7 seconds. Now, it was traveling for 9 seconds in total. That was the end of the journey. But the first 2 sections were acceleration. So we just want the second part of the journey from 2 to 9, 7 seconds. For question 4, again, we have an acceleration from 0 meters per second, getting faster and faster and faster, all the way up to 8 meters per second. And then it slows down all the way down to 0 meters per second. Now, we're being asked here, what was the top speed of the ball? So the fastest part of this is right at the top, the peak. We're being asked for a speed, not a time. So we're going to look across to the speeds. And the peak of the graph is at 8. So the top speed of the ball was at 8 meters per second. Now, for the final question, the ball speeds up from 0 all the way up to about 4.5 meters per second, but then it stays flat. Now, this doesn't mean that the ball is stationary, that it's not moving. It is moving. What this is showing us is that the speed is staying constant. So all the way through that blue section, the ball is moving at 4.5 meters per second, at the fastest speed it actually gets up to. So a flat section in a distance time graph is when we're stationary, nothing's happening. But in a velocity time graph, it just means the speed is not increasing or decreasing. It's a constant speed. It is still traveling. And then at 6 seconds, it starts to slow down again. 4.5 meters per second, down to 0 meters per second. Now, we're being asked how long was the ball at its top speed at a constant speed? And it started here, which looking down is at 3 seconds. It ended here, which looking down is 6 seconds. So in between 3 and 6, that is a length of 3 seconds. Now, for the medium questions, we're being asked what the acceleration and deceleration of the ball is. So the acceleration is where it starts to speed up, which I'm highlighting in green on the questions I need it for. And deceleration is where it's slowing down. So I need that for question 2 and for question 5. So we've already identified in the easy questions what acceleration and deceleration is. But what's the actual value it takes? Well, there is actually a way to measure it. And the way you measure how fast something is increasing its speed, you're kind of measuring the speed of the speed. So if speed is meters per second, then the speed of the speed is meters per second again. So we're kind of dividing by the speed twice. And so the way we show this is by writing meters per second squared. And the squared symbol just tells us that we're dividing by the speed twice. We've kind of found the speed of the speed. And just like something like miles per hour is a expression you can use, miles per hour means miles divided by hours. Meters per second squared is an equation you can use. Meters divided by seconds twice. So we are going to read off some values here. So for the first question, looking down, we start the acceleration at 0 seconds and we end it at 4 seconds. So it's been accelerating for 4 seconds. Then we look at the speed. So the speed starts at 0 seconds or 0 meters per second and it ends at 3 meters per second. So the top speed is 3 meters per second. So now what we do is we do the divisions. We've got meters per second, which is 3, divided by the number of seconds, 4. And that's going to give us the speed of the speed, the acceleration. And 3 divided by 4 is 0.75 meters per second squared. Now you might be thinking, it's meters per second squared. You said I need to divide by the seconds twice. But I only divided by 4 once. What's going on? Well, look at the units. If you look at the 3 is meters slash seconds. So the 3 meters per second is already being divided. We've already had one lot of division done for us already. It's there in the units, m/s. So then we just need a second slash s, which is when we divide by the 4. And finally, what 0.75 meters per second squared means is that every single second, the ball is getting 0.75 meters per second faster. So moving on to question 2, we want the deceleration of the ball to read off the values. So the deceleration starts at 5 seconds at the kind of peak of the graph, and it ends at 10 seconds. So from 5 to 10, that's a 5 seconds worth of deceleration. How much is it decelerating? Well, it's going from 2.5 meters per second down to 0. So we write down the largest value there, 2.5 meters per second. And then we do our calculation, meters per second per second. So meters per second is 2.5, and per second again, divide by 5. So this will be a calculator question, 2.5 divided by 5, and it gives 0.5. It'll be meters per second squared. And you think about it, there's a mental arithmetic version of that as well. We're thinking, how many 5s fit into 2.5? And half of a 5 fits into 2.5. So every second, the ball is getting 0.5 meters per second slower. Moving on to question 3, we want the acceleration of a ball. So we're going to read off our values. So the green part of the journey, the acceleration, is starting at 0 and ending at 2. So that would be 2 seconds altogether. And then how fast it's going? By the end, it's going 2 meters per second. So for the acceleration, meters per second, we have 2 meters per second divided by 2 seconds, and 2 divided by 2 is 1. So it's 1 meters per second squared acceleration. So every second, the ball is getting 1 meters per second faster. Same thing for question 4. We have acceleration. The acceleration starts at 0 seconds and it ends at 5 seconds. So we have 5 seconds of acceleration. How much acceleration? We go from 0 all the way up to 8.5 meters per second, with the peak of this being in between 8 and 9, so it'll be 8.5. Put that into our equation, meters per second squared. Meters per second is 8.5, and seconds again, that would be 5. So 8.5 divided by 5, that gives us 1.7 meters per second squared. Every second, the ball's getting 1.7 meters per second faster. And now for question 5. The deceleration starts at 4 seconds at the peak of the graph and it ends at 8 seconds. So we have 4 seconds of deceleration. The ball's traveling at 8 meters per second and it goes down to 0. So we have 8 meters per second of speed. Again, putting that into meters per second. Meters per second is 8, and per second again, that would be the 4. And 8 divided by 4 is 2. It's 2 meters per second squared of deceleration. Every second that passes, we're getting 2 meters per second slower. One extra detail, with deceleration, you can actually represent it with negative numbers as well. So to say, what is a deceleration? And I specifically said deceleration. I'm going to write 2 meters per second squared. But if I'm asked what's a change in speed, then I could say it's negative 2 meters per second squared because it's getting slower. Just be careful on the wording of the question. We can use negative numbers to represent deceleration depending on how it's worded. Now, for the final questions, we want to find the total distance the ball's travelled. But distance isn't on this at all. We have seconds on the x-axis and meters per second on the y-axis. So how can we get distance in meters out of this graph? Well, again, like I'm saying, these unit mathematical expressions you can use. Meters per second is meters divided by seconds. The slash means divide. So if I want meters on its own, I want to take meters per second and I want to multiply it by seconds. And what that'll do is the divide and times will cancel each other out. I'll just be left with meters. So that's what we're going to do. So how do we multiply them? Well, something else linked with multiplication is an area. If you find the area of something, you're multiplying two things together. So what we're actually going to find is the area underneath these graphs. So for question 1, we're going to find the area of the triangle where we have the acceleration. So in green, this is under the part of the graph where we're accelerating. Then we'll find the area in pink, the deceleration area. And together, that'll be the total distance travelled. So for the green section, the meters per second is 5. That's the peak of the graph. And the number of seconds that lasts for is from 0 to 4. So that'll be 4 seconds. So you might be tempted to do, okay, so we have meters per second, so that's 5. And it's going to be 5 multiplied by the number of seconds, 4. And 5 times 4 is 20. And you'd be close. But it's not quite going to work like that, because if we did 5 times 4, what you are saying is that it's been at 5 meters per second for the entire time. But it hasn't. It's only 5 meters per second at the very end. At the start, it's 0 meters per second. So we have to do something to adjust for this. And the way we adjust for it is we look at the shape. The shape is a triangle. And when you find a triangle, it's base times height divided by 2. So we have the base 4, we have the height 5, but we need to divide by 2. Because again, it hasn't been 5 meters per second for the entire time. So 5 times 4 is 20, and divide by 2 is 10. So it's going to be 10 meters travelled altogether. Where that number comes from might make more sense if I cut this triangle up into strips. So what we're saying is right at the start, I was colored part of it in purple. For the first second, the ball's not actually travelling that far. It's only travelled maybe 1 meter, because the ball isn't travelling very, very fast. But for the final section, which I'm also colouring in purple, we can now see the balls travel a lot more ground. It's going much, much more quickly, so it's travelling more ground. So again, the divide by 2 just kind of evens out those two extremes, where at the start it's not traveling very fast and very far, and at the end it's traveling much faster and much further. So now we've found out that the accelerating section, we've traveled 10 meters. We do the same thing for deceleration. So it's starting at 5 meters per second, and that's lasting for, again, 4 seconds. So we do the multiplication of 5 meters per second, multiplied by the number of seconds, 4, to get to meters. But then remember that it's traveling at 5 meters per second at the start, but it's traveling at 0 meters per second at the end. So we can't just do 5 times 4. We have to adjust for the difference in speeds. Because it's a triangle, we can divide by 2. And that gives us another 10 meters traveled on the way back. So what was the total distance the ball traveled? 10 meters plus 10 meters gives us 20 meters traveled altogether. So let's do the same thing for question 2. We have the acceleration section. We have the deceleration section. So let's find those individually. So for acceleration, it's going up to 4 meters per second. And for deceleration, we'll be using that as well, because that's where it finishes for acceleration and starts for deceleration. The acceleration section lasts for 2 seconds, between 0 and 2 seconds. The deceleration section, though, it lasts between 2 and 5 seconds, so we have 3 seconds of deceleration. So for our acceleration, meters per second multiplied by seconds gets us 8 meters. But remember, it's a triangle shape, we're going to divide by 2. So it is actually going to be 4 meters altogether. But for deceleration, it's 4 meters per second, but it's multiplied by 3 seconds to get our meters. But again, the answer is not 12. We have to adjust for the differences in speed from the start and the end. It's a triangle shape, so we divide by 2. So that's going to give us 6 meters altogether. So actually, the ball travels more distance while it's decelerating, because it's decelerating more slowly over 3 seconds. So 4 meters while accelerating, plus 6 meters while decelerating. Altogether, the ball has travelled 10 meters. Question 3 works the same way, but I'm going to show you a little shortcut now. Now, rather than finding acceleration and deceleration separately and getting 2 triangles, you might have noticed that the whole thing is a triangle. So what we could do is that we could just find the area of the whole thing, and that is actually going to work out. So as a shortcut, the area of the entire triangle, it starts at 0 seconds and ends at 10 seconds. So that's 10 seconds of travel altogether. The peak is at 6 meters per second speed. So we can do 6 meters per second multiplied by 10 seconds just to get meters. That's 60 meters. But again, the speeds vary all the way through. 6 times 10 would represent it being at 6 meters per second the entire time, and it's not. But because it's a triangle shape, we can divide by 2. So 6 times 10 is 60, divided by 2 is 30. So what was his total distance the ball travelled? 30 meters. So if you are confident and you can spot shortcuts like that, you are welcome to use them. Now, going back to our individual shapes, for question 4, we have an acceleration section that goes from 0 seconds to 2 seconds. That's 2 seconds of acceleration, and it goes up to 2 meters per second. But after that, we have something new. We have a period of constant speed. And from 2 seconds all the way up to 7 seconds, the ball doesn't change speed. And it's important to note it's not stationary. This ball is traveling at 2 meters per second the entire time. And it's doing that between 2 and 7 seconds, which is 5 seconds of travel at that speed. Finally, at the end, it does decelerate. It starts its deceleration at 2 meters per second, and it decelerates for 3 seconds. So let's work out all the individual sections. So the acceleration section, 2 meters per second multiplied by the number of seconds, but it's a triangle shape, we need to divide by 2. That's 2 meters travelled altogether. The blue section, 2 meters per second for 5 seconds. Now, for this, it is actually travelling at 2 meters per second the entire time. And it's a rectangle shape, and for a rectangle, it's just base times height. There's no divide by 2. So that is 10 meters travelled. And then for the deceleration, 2 meters per second, lasting for 3 seconds. Again, the speeds do vary. It's a triangle. We're going to divide by 2. And that gives us 3 meters travelled. So altogether, we have 2 meters plus 10 meters plus 3 meters. That's 15 meters travelled altogether. Moving on to question 5, we have another section that has a acceleration section, a constant speed section, and a deceleration section. And so we could use a method question for split it up into 3 parts and work out all 3 parts individually. If you're feeling more confident, you'll notice that the entire thing is a trapezium, and you might remember the trapezium formula. And you can actually use a trapezium formula to work out the distance travelled, and that'll work just as well as finding 2 triangles and a rectangle like we did with the previous question. So for a trapezium, we're travelling at 7 meters per second by the end of the acceleration. So that's the height of the trapezium. Now, when we do base times height for a four-sided shape, we'll see the base is 10 seconds from 0 to 10. But this shape effectively has 2 bases. A trapezium has a second base, and at the top, we're going from 4 seconds to 6 seconds. That's a 2-second width at the top. So we've got 2 widths or 2 bases. And quadrilaterals are base times height. So you might remember from trapeziums, because it's got 2 bases, or rather 2 widths, you can just average them out to do base times height. So what's the average of 2 and 10? So to find the average, add them together, 2 plus 10, divide by how many? There's 2 of them. So 2 plus 10 is 12, and divide by 2 is 6. So on average, we've got a width of 6 seconds. So now we can do our calculation. We need a base, 6, times the height, 7, and 6 times 7 is going to give us 42. So what's the total distance travelled? 42 meters. So to sum up, to find the total distance travelled on a velocity time graph, find the area underneath the graph. And you can do that by splitting it up into multiple shapes, multiple triangles and rectangles, like we did for question 1, 2, and 4. Or alternatively, you can find the area of the entire shape all at once if you're confident with your geometry. You will get the same answer for both ways.